This is the Math Map Book Club, where ordinary parents encourage one another to develop an extraordinary appreciation of math. We love what we know and struggle over the unfamiliar. Through weekly conversation and exploration among friends, we can begin to enjoy ideas that seem difficult. Join our book club as we discover how math helps us to know God and to make Him known.
Hi, I'm Lee Bortons, and it's Wednesday, September 25th, 2024. Welcome to the Math Map Book Club, where Kirsty Gilpin and I discuss lessons each week from our math curriculum for families with students enrolled in classical conversations communities. And today we have a special guest who's going to help lead us, Jill Philbrook. She's been with the Math Map, helping us as a parent, tutor, pilot, developer, all around just a support person since we began almost 7 years ago. So Jill, welcome, and I'm so glad that we have folks like you to show us that you don't have to tutor the way Kirsty does or the way I do. There's all kinds of ways that will help your students connect with math. And so thank you for being here today, and I look forward to listening to this later, because since you're here, that frees me up to go ahead and meet some more Math Map deadlines. For those of you that are interested, we're in the process of getting 4 new domains out in the next month. And so there's a lot to do. So thanks so much, Jill, and thanks so much, Kirsty.
Thank you. I'm glad that I can help, and it's exciting to see you again and to know that you get to do some things. 4 domains is awesome. And I didn't know if Kirsty had anything she wanted to say before I start.
No, only to echo the fact that Jill is amazing, and Jill and Babs together, like if I could have hand selected any tutor for my kids, it would have been one of them. And Jill has always amazed me with her real grasp of the classical model and bringing that into her Challenge A classroom. And so I just know that she's going to bless all of us today.
Well, thank you so much. I am living proof that you don't have to be what people might consider a math person or strong in math to enjoy math, to love math, to lead math. And so I hope you are settled in for a wonderfully not perfect person, a wonderfully not perfect mathematician who has a lot of enthusiasm about math so that we can learn together. So we'll jump right in. In my Challenge A class, what I normally start with, just like Dr. Gilpin has and Babs and others, is we start with our booklet. We get out our booklet, make sure we all have the right booklet. So this week we're on booklet 9. So everybody should, if you have a booklet, you should be looking at a booklet that has a flamingo on the cover. For a moment there, the bird name flew. So then we will open it up and we'll find our spot on the map. So if you are in a Challenge A class, you are in this gold complex column. And exciting times, we are finally into a new domain, a new dimension, not a new domain, a new dimension. We're in 2D, and so we are on booklet 9 right there. You see where it's already been used with a highlighter. And some of my kids, now we finally get to make our own check marks. Some of them follow the pattern that we've been doing and all the check marks all the way down. So every week we have to do all the check marks all the way down, and others like to do it their own way, put a face on it, a check mark on it, whatever they're going to do. But it is nice to see that progress. Sometimes I think we would benefit by seeing that progress in our life in other places as well. Have that thing that shows how far we've come. So we found our place on the map, and we will go ahead with our cover. Oh, I'm sorry, number knockout. So we have our timer set here. So just start calling them out, and Kirsty's gonna knock them off for us. So just shout out what you see. We're using 2, 1, and 6 today in case you're driving and not able to see the screen.
Well, 2 plus 1 plus 6 is 9.
Because they were innocent, period. I know there are people who want
6 squared is 36 minus 1 minus 2 would be 33. And then you could also do the 2 and the 1 to powers of 0, and you could get 34 and 35 as well. And you could multiply by 36 and get 36. So that wasn't
Awesome.
clear the way I said that, but Thank you.
No, that's great. Yes, my students always ask, do we get to use Paro Zero? Because sometimes I make them hold off for a few seconds first.
6 times 2 is 12, plus 2 is 14, plus 1 is 15, minus 1 is 14.
2 times 1 is 2, plus 6 is 8.
Nice.
2 squared is 4 plus 6 is 10 times 10 to the 0 equals 10.
Excellent.
2 times 6 is 12, plus 1 is 13.
Very nice.
2 plus 1 is 3, times 6 is 18.
2 times 6 is 12, minus 1 is 11.
Mm-hmm.
2 to the 1 times 1 to the 1 times 6 to the 1 is 1.
Nice.
I'm sorry, to the 0.
2 squared is 4 times 6 is 24 times 1 is 24 plus 1 is 25 minus 1 is 23.
Very good.
2 times 1 times 6 is 18.
Excellent. We're getting there.
6 minus 2 minus 1 equals 3.
Very nice, and just under the wire. So one thing I like to do with my class is have the students do what you all were doing, which is say the whole thing so that I can keep up, because they can just shout anything. And when you're up at the board and they're shouting all kinds of things, you take their word for it, and they may or may not actually be knocking out the number they say they are. So I like when they follow the whole thing, you know, and say the 6 squared is 36, plus 2 is 38, minus 1 is 37, which is not on the board. Because that's how you find out if they're doing it right or not, if they're actually coming up with the things. If I'm doing this at home with my kids, if they're young, I will sometimes even write out math equations for them to solve, to help us knock them out. Whatever it takes, just to kind of partner with your class or your own students at home, wherever they are. Also in class, if I have a few kids who are further advanced than others and they're really speedy on this, I might tell them all for 15 or 20 seconds to hold, just to not say anything, to write down as many as they can. And then I try to call on those kids who don't have as much to say or don't get to say as many things during our timer, because other kids are quickly shouting them out, and it gives those quieter kids a chance to say first a few of the things. So that's some of what I do. So we can move on now, and we're going to take a look at our cover. So as we look at this cover, it's very interesting, and I've had a lot of feedback from the kids over the years about this picture and this title. What title do you see? What picture do you see? And what are your thoughts?
That's American flamingo. So I'm like, is that because he's in America, or are there different flamingos that are distinguished by their country?
That would be a great thing to write down on the cover, and to maybe let them, especially in Challenge A, if they haven't got, well, they've probably already done birds, but you know, this might be something they want to learn more about or hand off to their sibling in foundations.
I love that he, I think this is Audubon, right? Yeah. He is able to contort the flamingo into a position that you can see it in the full body of the flamingo, but it fits within a particular space. So that's impressive with the all the angles and the curves that he uses to capture that whole bird and in that frame. So yeah.
Yes, I agree.
I think I'm going to hear, where are the straight lines at?
Right, you probably will. So where do you see straight lines, and where does it look like there aren't straight lines?
Well, it seems like that front leg that's bent is an angled line, but really it's made up of 2 straight lines.
Yeah.
There are some
And
straight.
even the neck, wouldn't that, I mean, it can also straighten out. So it's probably not made of a curve. It's probably made of a lot of straight parts of the neck.
So in the
Is-
webbing of feet, there's some the straight
Ah, yes,
webbing of the feet.
right.
On the leg,
Horizon
there's a
is a
straight
straight
line.
The horizon is a straight line.
Yes, and there's some pictures at the top that, depending on your screen, you might be able to see or not see some sketches that go along with it where you can see those are made of some straight lines too. Is there someone who would read the quote and the quotation for us? Just one person each?
We are so made that truth, absolute and certain truth, is a perfect joy to us. And that is the joy that mathematics afford. Charlotte Mason.
Does someone else want to read the reflection, and then we can talk about both of them?
Here we are before thee, O Holy Ghost. We feel the burden of our infirmities, but we are united all together in thy name. Come to us, help us, enter into our hearts. Teach us what we should do, the path to follow. Do for us what thou askest us to do. Isidore of Seville.
So what do you see in common with these two things written at the bottom here, the quote and the reflection?
Well, I could see truth as being a straight line, kind of in a way, like I don't know, like the narrow path, whatever, that
Right.
Jesus refers to truth. And so it's like in that second one, it's like, teach us the straight line, because in the first one, we love the straight line. I don't know.
Yes. Yeah, I agree. And in the first one, we're talking about this absolute joy and certain truth. And then in the second one, we're talking about where it can be hard. But then we're saying, if you'll help us, if you'll teach us what to do and the path to follow, that kind of points back to that joy again.
And
In
I
our
think,
devotions, go ahead, someone else.
well, I just think of that perfect joy to us. And then the line from the reflection that says, we are all united together in that name, that those can be synonymous, that we find joy in being united together in him, despite our infirmities.
That points back to, somebody might say, hey, that reminds me of the power of zero that we did back in exponentiation. If you've heard Kirsty share about the power of zero and how laying down our thing unites us and makes us one. And so that idea that we can set aside our infirmities or our great things, not only our weaknesses, but what we think makes us extra. And then we can put that down and we can be united together in him. Anything else?
I saw the connect to Mr. Bowditch. That was his joy, that it was just math. It was always this way, it was a certain truth.
Absolutely. He loved to have something reliable.
Jill, I love when you pointed out, because it was something I had not really thought about before, but when you talked about the fact that he had those sketches at the top, right, that we tend to look at the finished product and go, wow, that's just so beautiful. But his finished product includes his side work and his practice. In math, there's so much practice and so much side work. And sometimes we only assess on the finished product, right? We think it has to be perfect, but it's that side work and that practice that maybe is imperfect that gets us to that finished product. And so I was just encouraged by that our side work and our other work is just as important as that finished product.
It really is. And I remember times that side work and that practice work mattered so much, especially if my child was learning how to make letters or numbers and learning how to make them legible and also doing math or writing words. But if they were trying to add, and some of their numbers, if they had like an amazing 5, one of my kids in particular would be like, Mom, Isn't this the most beautiful 5 I've ever made? And you know, it goes back to the classical model and that doxology. Take time to celebrate that. Take time to celebrate what our students see in the art. Take time to celebrate the connections that they made and noticing what straight lines are and what a bent line, and that a bent line is actually 2 straight lines that are connected at a point. Those kinds of things. I think that's part of what brings the joy of anything we learn, but specifically math. Sometimes you celebrate that that was the most gorgeous 5 you ever made. So we can go on to our next page. So we're here at invention, and in my class, I like to first point them to something to start with. And so in my class, we probably would start with this upper left box. So we have a few sentences here. We have, let's see, 1, 2, 3, 4 sentences. So would someone please read the first sentence out of that box on the left?
2D is a plane represented by an intersection of 2 orthogonal axes.
So is there a new word there for anyone, for any of our 7th graders?
I'm guessing orthogonal for them.
Yes. So I learned from Kirsty, because I did not know, that it's orthogonal. So I'm just
I
giving
wondered
you
if I
that
was saying
heads
right.
up,
Thank you.
because I did not know until the math map. I'd never seen that word. I probably would not have known what category to put it in, but orthogonal. So if we see here that this plane is represented by an intersection of 2 orthogonal axes, and we see this picture, what might we think orthogonal means?
Perpendicular?
Yes. And so what degree would perpendicular be?
90-degree angles.
Right. So what we've seen here is that there's 2 intersections, that there's an intersection of these 2 orthogonal perpendicular 90-degree angles. So that's either review for some students and their vocabulary or new vocabulary for others. And it's the kind of thing that's going to take them through this whole booklet. How about someone read the next line?
A plane is that which has infinite length and infinite width, but no height.
So what do we think about when we think about a plane, Plane, having infinite length and infinite width, but no height? What do we picture?
A wall, a grand wall. No,
Yeah, exactly. You would never get to the end of it. If you had to paint that, it would go forever, forever. So one thing that I had found very interesting is that it's talking about infinite length and width, but no height. And when I'm writing on the board, it's very easy for me to always picture this is the whiteboard, by the way, my axis, my coordinate plane in 2D as vertical, because I'm writing it all on the board. But if we look at it this way and we see that it is infinite length and infinite width, but no height, it's actually flat this way. That would go on forever. And when we add our 3D and we start talking about adding height, that will make sense when we have this pencil that we put up through the top. So just thinking about that, because sometimes our kids will be going, what do you mean it doesn't have height? It's right here. But if we lay it horizontally and we think about that plane with going forever this way, then that can help them later. It can help them when we get to 3D.
So if we picture more like the land and how it lays out before us, it goes on forever in front of us and beside us. Okay.
And really,
Right,
since
because
we're talking about 2D, it's not that it really matters how it's positioned, but it's just like you were saying, that word height can make it confusing if our images don't line up. But
yes, because sometimes I've done this in my class too. I've said, well, let's actually see, well, we can do it right here. I've had them hold 2 fingers and say, okay, so if you've got these 2 fingers, it doesn't matter where you hold them. It's one line between them, right? Like you could have even a string where, however you hold these 2 fingers, it's one string. So that could be a 1D. But when we go to 2D, then this plane, this piece of paper, it doesn't matter what direction I hold this, it's still one plane. And it can have any 2 points on that one plane. But if I'm looking at it with length and width, then it's easier to think of it flat this way. And then if we read the next sentence, we'll understand more about that whole plane and what it takes to define a plane. So will someone please read that?
3 non-collinear points define a plane.
So if we think about linear and non-collinear, or collinear and non-collinear, what would that be new to some of our students?
Maybe the vocabulary, but is it not parallel?
So collinear, if you think about that string, everything on that string would be in the same string, right? On the same line. So that would be collinear. In order to define a plane, because if I just do 3 dots on this paper, I could rotate this any way, and it would be lots of different kinds of planes. But if I have a dot here, here, and here, that defines what plane I'm talking about. When you have 3 dots, if you make 3 fingers, 3 dots, then if you think about what would make it flat against that, however you hold it, you could hold something flat against all 3 of those points, and that's the plane. But you have to have 3 minimum, and they cannot be all in a line. Because if they're all in a line, it's just this long wash line that something could be spinning around in any direction. So that's something I would probably do hands-on with my class. I might even hold a string, and I might hold something flat against it and show how that I could have this booklet up against it going lots of different planes. It could be here, 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 all on that line. But if I have the 3, then I might even have 2 kids hold up 3 fingers and somebody else hold something flat against it. Does that make sense? Or is anybody saying, no, that I don't know what you're talking about and this is not good?
Yeah, I like it.
Okay, good. All right, so let's look at the next sentence.
Second power of anything squared, a squared, can represent an area.
So most kids are pretty familiar with the idea of a square, the area, right? So I would only probably spend extra time on that if it seemed that someone really needed it. If the kids were not familiar with that, I might talk about area and, like square inches. I might show them on my whiteboard how many squares. Okay, so this would be 4 squares, right? 4, and if each one is an inch. But most of our kids have probably already looked at area before. All right, now, Kirsty, do I have time to stay on this page a little bit longer, or do I need to move on?
Not really. You really need to move on.
Okay, all right. So that would be, I think, still a very powerful thing for my class, especially if that's what they needed. If they didn't need that and they were already comfortable with that, if it was their second year, I would go down into the difference in the polar coordinate plane and the rectangular coordinate plane. So now we'll look at our Memoria page. I also might ask my kids to get out a piece of paper and write down, draw a coordinate plane, or I might have them get out their whiteboards, and before I show them this page, ask them to label anything they can think of that would go on this whole thing. What do you already know? Because this is Memoria, right? We're talking about what do you remember? And so some of these words they might know their quadrants. If they don't know this, we might take a minute and I might have it on the board with a big X and we might go up there and label it. Or we might just get out our highlighters and highlight what is new to you here in this image on your I3 Memoria page. So does anybody see anything that's really familiar or really unfamiliar, even to your student? Think like your 7th grader. What would be unfamiliar to your 7th grader?
Probably mine, the rise over the run, the slope.
Okay.
Axis of say.
Yes, so the this would be, I guess, the plural, right? So I know it as the abscissa.
Okay.
And the ordinate, the X is abscissa and the Y is the ordinate, but it's plural. Here it says axis of ordinates, which I'm Kirsty, can you help me? Would that be all vertical lines and all horizontal lines?
So the abscissa is our horizontal coordinate and our ordinate is our vertical coordinate. So our axis of the abscissa is essentially the x-axis. It's whatever variable we're using is the name of that axis. And then our y-axis would be our ordinate, our axis of the ordinate, or whatever letter we're using, right? So we are so conditioned to x and y, but one of the reasons I love lesson 24 is because I think it's really a great opportunity to practice with all different kinds of letters. So we might have our independent variable or our abscissa, maybe time that we use with t, and then our vertical, our ordinate coordinate, maybe our x coordinate in that case. So abscissa and ordinate are just good words because they're the generic horizontal and vertical coordinate words.
Awesome.
How come one has
So,
a AE ending like you know, like this
It
this
must be
declension Latin now?
Latin, yeah, singular and plural.
it can also be genitive. But if you think about that, AE could be genitive. So that could be where I was thinking plural, but it's the axis of. So it's of the X. So that AE could be genitive.
I think it's plural because if
Oh,
we
well,
compare it to axis of ordinates,
there you go.
that one's plural. That would be a great
See?
comparison question for students to
Such a
compare the
great
two.
comparison.
It
Yeah.
would.
And
'Cause the
challenge A,
plural-
where they're becoming so familiar with spotting Latin all around them.
Yes, because the plural is what made me think, well, is it all horizontal lines? And your student might ask that. So we just definitely had a conversation that some seventh graders might have. Is it all horizontal lines or what is this AE? So now we know it is the x-axis, the y-axis, also called the abscissa, and the axis of ordinates. Anything else that your seventh grader might be familiar or unfamiliar with on this, all this great information on the rectangular coordinate system?
See a lot of the cards from the notation flashcards. A lot of
Yes.
words, quadrant, delta.
Yes.
They might not be familiar with the naming of the quadrants and how they go counterclockwise.
Yes. Exactly. So you might even start having them high five each other in that order. Dun, dun. And you kind of want to go 1, 2, 3, 4, but that's not right. So you have to, 1, 2, 3, 4, or dance steps or whatever you got to do. We've done footwork on the floor with the 1, 2, 3, 4, and you having to move your left foot from the front and then back instead of right, left can be, it's a chance to get up and move a little. Anything else?
I think
Here's the question I have as a seventh grader. We talked about the planes as having no height and that it was width and length. But yet when we talk about the plane on this grid system, we're referring to the axis of ordinate or the y-axis vertical. And I would think of vertical as height.
I would too. And I guess I shouldn't have said vertical because that is what did that. And so I would tell my class, I'd say, yep, you're right. I used the word vertical. What we need to keep in mind is that in our head, we're looking at this and it can go in any direction. But really, it's not necessarily vertical. And the word rise over run is going to sound that way too. So I think just identifying that we know that those words sometimes look like they overlap and expressing with them that we have to sort that out in our mind as well can help them to go, okay, I'm going to put that in the same box and realize that it's not perfect in my mind. And I have to know the relationship, the circumstance, the context of what it is we're talking about. We won't necessarily have a perfect answer.
I'm going to share a story and then I'm going to push you on to the next part of our class. But when we talk about vertical and horizontal, right, they are words that describe a relationship. and not a fixed location, right? So a lot of the times we think of vertical as being upright because we think of horizontal when we lie down, right? And so I stand up and I'm vertical, and that's how we use it in 3 dimensions. But it's always relative to something. And so when Lee and I first started talking about the curriculum, and she would be writing, she would say, well, it's a vertical line. And I'm like, no, there's only one line in 1D. It can't be vertical. She goes, well, what about the horizontal line? I said, there's only one line in 1D. It can't be horizontal. It's the only line, right? So now all of a sudden I can describe, if we're going to say that X is horizontal, we can say that my Y is vertical because it's in relationship to that, right? So that's our 2D understanding, right? And then when we get to 3D things, we suddenly now go, okay, well, now what do I really mean, right? Because which one am I describing? And we have to be really clear. So sometimes our everyday English and our math English, there's a little bit of a disconnect because we are so used to using words in our 3D world that we have to kind of pull back and go, okay, well, what is it that word really means? So just as Jill said, right, these are brain stretching ideas and brain stretching words. They are things that Lee and I wrestled with. And even when we're looking at a page, right, we usually think of the bottom of our page as being our horizontal and the side being vertical. So when I describe things that are on the page and I say read horizontally, what do I mean? When I say read vertically, what do I mean? And again, it's always relative. So you're not the only ones.
That's really
Thank
helpful.
you.
I
Yeah,
never thought
yeah.
about them being fixed and that instead they were a relationship. So that's brilliant. So we will look now at the chart. And since we already looked at the coordinate system up in the top left, top right corner, let's compare now our rectangular coordinate plane, our polar coordinate plane, and our complex coordinate plane. So we might take a look in this middle section right through here, and there's a great comparison chart here of 0D, 1D, and 2D. So most kids are pretty familiar with the rectangular coordinate plane. They have graphed or plotted something at some point where they had to go over on the X, up or down a certain number of spaces on the Y. But we might ask them, so what does a polar coordinate plane remind you of? Does it look like anything you've ever seen before? Maybe in a movie.
Oh, I was thinking the bottom of a globe. When you look at the Antarctica, you look at it like from the bottom, and so you just see this round shape. You don't see the shape of a sphere.
Exactly. In their cartography book, that would be how they're going to draw Antarctica when they get to that page, right? So yes, it's going to be, we're looking at something that has a roundness to it, maybe not a spherical, but round. And maybe they've watched some submarine movie, right? So if you're in a submarine and you're going along and you're trying to find something, and you might not have a coordinate plane, a rectangular coordinate plane, but you have a polar coordinate plane. So you need to know a couple things. You need to know your distance across, right? So you can, if you have this X, instead of having an X and a Y, the whole thing, we're looking around this whole X. So do you see that on the circle where it says that X is that an X there? An R is a subset of real numbers, right? So your radius is going to be how far, but that's this. Well, what are you going to do about this? So if you need to get, if this is you, the submarine, and here's this point, but you want to get up here, what possible measurement could you use? And if they've read Bowditch, they might be thinking, oh, well, he had to think about the angle, right? Up to the moon, to the stars. And so not only do we have our radius, but we have an angle. So we know how far and we know the degrees up. And that is going to be called theta. So they've learned theta, and they've probably seen that on some of the flashcards and some other things that they've done. But instead of having an X and a Y, we're going to have theta and a radius. So I would practice with that on something plain, anything whatever we can do. I might even have string, and we'll measure around and we'll draw this and practice and get them comfortable with that idea. Now the complex coordinate plane. This is what's a little interesting. What do we see here as the labels on our complex coordinate plane?
A real number line and an imaginary number line.
Yes. And what is different about this is that this a plus bi, so any number on the x and any number on the I, is only one number. It's the whole thing. It's like, it's not just the a and it's not just the bi. That whole thing together is one number. Is that new to your 7th grader? It might be. It's kind of like dollars and cents. It's one amount. The store does not charge you $7 and then also charge you 12 cents. The whole thing is the amount, the dollars and the cents together. Only with this, it's the real and the imaginary together that create one number.
Which we have talked about in previous weeks. Like maybe the concept hasn't done the light bulb thing yet, but we have worked with.
And now they're graphing it. So we're still looking for the real part and the imaginary part, but when we get there, it's one number. When we find that spot, it's one number. So we can look here at this page, and is there any, as you're scanning or as you were looking, were there any definitions or new things that you think, okay, I need this for this lesson? Yes, it is like the complete expression. I think I'm saying that right. Kirsty can tell me.
Yes, that's what she means, is that sum of 4 plus 3i is one number.
Awesome. Anything else on this page that you would want your student, and I love using highlighters in the book. It helps me a lot. It helps me highlight what I want to know, or sometimes I might highlight what I already know. And I might challenge myself to find just 2 new things, not the whole chart. And I have often told my kids, especially if they say, oh my goodness, this is so much. And I'll say, this is for 12th graders. This is still a goal for 12th graders. I don't know all this, and you are not expected to know all this, but we're not hiding it from you. We give you the whole Bible, the whole thing. You don't know it all, but it's all for you. And you don't know all this chart, but it is all for you. It is to bless you. And so sometimes they don't believe me, but deep inside, I think they do.
The analogy.
I think it's really beautiful at the bottom of the page where they made you do the hops, because when you're looking at rise over run, it kind of helps you to imagine the upward thing of the rise upward on the page if we're talking about perspective or circumstance, and then horizontally on that axis. I think that was really good for the kids for my brain too, for us to understand the concept of the differences between the rise and the run.
Awesome. What page are you on? Are you on the chart or are you on a different page?
You're muted, Tanya.
I didn't see it on the chart, but I do love the hops idea. Are you looking at the second
No,
chart?
I'm on page 1.
Oh, okay.
Is everyone else on page 1 of the chart? You know.
I think so. Yes.
Okay, because what you were talking about, I was looking at the polar thing on the top of page 1 too. When you were talking
Well, it's
about
still
that.
they go
fits,
together.
right?
It's
Yeah,
in
they go
multiple
together.
places. See, what a blessing.
It is. It is. So the other big idea for this week, I would say, is whether you have a positive, negative, or parallel, what you're doing with slopes. So if you look over at the second chart, thinking about going uphill on a roller coaster or downhill on a roller coaster, something that they can just think about, is this going up? Is it increasing or is it decreasing? You can have a lot of fun with that. So any thoughts that came to you initially when you see the positive, the negative, and then these parallel lines in regard to slope?
I always think about energy when I'm thinking about the direction of slopes and how it's required energy to go up against gravity, or if you're going downwards, in perspective on the chart, then it's a less energy required.
That's really good. And then if you compare those, you see how it's color coordinated. The blue, the red, and the green is color coordinated to m, which equals slope, and whether it equals 0, whether it is less than or greater than or equal to 1, so that you can see what's happening there. And for them to make that distinction and take a moment and just look at it and think about what it means and copy it if necessary.
All right, Jill, I'm going to move us on, but while I'm moving us on, I just wanted to jump in and emphasize something that Jill said to you. She said that she likes to highlight her charts. And we've seen a number of really helpful moms that have produced content about the math map that have never used the math map. And they're suggesting that you take all your charts and you put them in page protectors and you keep them pristine and beautiful. And I just want to encourage you that that's not really what our intent was. Our intent was that you hold on to those charts and you use them, highlight them, make notes on them, circle things that don't make sense to you and you want to come back to, or like draw a smiley face on something that clicked. And then next year, you can go back and you can look at that and go, hey, what did we leave from last year for this year? Or what went really well last year that I can build on? And so I just want to encourage people to feel like those charts are a usable resource for you, that they are there for you to take notes on, pull them apart, do what you need to do to make them work for you. They don't have to be kept pristine because you're going to get a new set next year. And so I just wanted to thank Jill for talking about how she uses the charts in a practical way, and really encourage everybody to feel like this is a resource that you can use in that way. Right now, Jill's going to answer all your questions about exponentiation.
All of them, every single one. You can laugh longer if you want to at that. Did anybody have a question? I don't think they did. I think we're
Well, if you would like, we'll go ahead and we'll move on to looking at our page tops. And then if you have questions, we can address them all at once at the end.
That's probably a great idea. So if we take a look here at our page tops, you'll see that we are looking at geometry, which is a lot of fun, and it really is much more restful to me than arithmetic. So one thing I have noticed is that the first 8 weeks have, for my families, been the most frustrating and the hardest. It is a whole new way of looking at things because we hear words like add, subtract, multiply, divide. We think we know those things. We think we already know addition, we already know subtraction, multiplication, and division. And so when we have to do it in a new way, and when we think harder, and when we stretch what we're doing, it feels difficult. But it's just that it can go deeper. There's more to addition than what we thought we knew. There's more to subtraction. And so when we're in geometry, we're back in shapes, which is a happy place for a lot of us. So I hope that week 9 does become restful for you, that you're back in the land of shapes and you're not having to think about addition in another way. So if we look here, we see our X and our Y, and what are the directions? It says study, rectangular to polar to complex, label delta Y and delta X, which would be change in Y and change in X. And that's only over there in the far after the line. So in the first 3, they're asking us to study. What do we notice? We notice that we are in a real domain in the coordinate rectangular. We're in real domains in the polar coordinate system. And when we move to the complex, we have a real and an imaginary, right? And then we're studying these labels. What are the labels we see? Anybody want to say the labels you see all the way across?
We have an XY in the first, and then in the second one, we have just an X axis, but then our radius and theta. And then our labels on the last one are real and imaginary again.
Right. So I would probably have my students circle those, highlight those, color code those, and pointing out that that X, why we only need X is looking at the degrees, the 0 all the way around to the 360. And then we see our coordinates. So in the first one, we have the XY. In the second one, like Jana said, we have the radius and theta. And in the third one, like we've talked about before, we have our real number and our imaginary number. So we have the A, which is our real number, which corresponds to what we're used to doing on an x-axis. And we have any number on the imaginary axis, which corresponds to what we remember about y's, but we're putting it together into one number, the real and the imaginary part. And then we're looking at the next one, all the way to the far right. We're labeling our change in y and our change in x. Do you see any change in those lines?
I have a question about the polar coordinate. I'm sorry.
Yes.
Where it says, you know, the axis labels is x, but is x the same as r is the radius, right? It doesn't matter what angle it's at, x will be r.
Well, x is the whole line.
So
R
it's
is
the
going to be
diameter. Okay.
right.
Okay.
Right.
Okay. Thanks.
So Jill, I had a question about that as well. So looking at the X, is the X-axis only the line segment starting at the origin and going at 0 degrees, or does it also include the other direction?
It would include the whole thing, the whole line, all the way through the circle, out the other side, unless I'm wrong, in which case Kirsty needs to be shaking her head emphatically.
So you're right that when we think of it being an axis, right, the whole thing is there, but we don't really need it because we're not using it like a coordinate. It's just our reference. And so we think of it as that positive x-axis mostly because it's going to help us down the road to kind of overlay the two and be able to change from one system to another. But we don't use the x coordinate. It's just our reference point. It's sometimes called the polar axis, and all it is there is to tell us where we start measuring our angles from. So it's our 0 degree, it's our 0 degrees. That's why it's there. It's not exactly, it's not a coordinate. So notice that's why our coordinates have nothing to do with x. They just have to do with r and theta.
Okay.
Awesome.
So that explains then why that vertical line and to the left of the origin, those are dotted, not a solid line. Is that correct?
Correct.
Okay.
Those are there for our reference because if all the kids saw was a line with 0 degrees and an origin, they'd probably like, well, I don't get this. So we've added more just to help the students see and give them a reference as to where 90, 180, and 270 are and how we would put a point out there as r theta. Because we wouldn't even
That's
actually
not just
have
for
to
the
draw
kids.
that radius in. That's just there to help us too.
Yes, as that's for the adults as well.
So could we make a comparison between the origin on a number line? So you have to start someplace so we know how many hops or what the measurement will be. The same with this on this polar axis. You have to know where to start your measurement from.
Yes.
Yeah.
So can I ask for a little bit more clarification about what the XY and the XY in the rectangular and then the X in the polar, they do or do not coordinate with the coordinates? I think I'm still kind of stuck on how X correlates with the R theta as opposed to XY correlating with XY in the rectangular.
Sure. Do you want me to? I'm sorry. I'm jumping on top of you.
Sure,
Jill.
go ahead.
So that X, we call it X to really emphasize that we're looking for that, essentially that horizontal piece that's there. Because I always like to think of polar coordinates as pirate coordinates, because if you think about, they usually think about, okay, find the tree, and then you stand there and it says take 4 steps forward. That's my radius, right? And then it says towards the rock. And so I know I need to turn my body and face the rock and take my 4 steps. And then it might say, look for the skull in the branches or something. And so now I'm going to
That's good.
turn, and then it says take 8 steps, right? So all of that is referenced off of me and where I'm looking, and radar works that way, right? So it's like wherever I'm looking, and my degrees work from that. But when we're talking about polar coordinates, we need to fix that so that we're all talking about the same thing. Because if we were all standing next to each other and we were all using ourselves as our origin and turning, you know, the same, we could all turn the same degrees and we could all walk the same number of steps, but we'd get to different places because we started in different places. And so we need to fix, when we're talking mathematically, right? We need to say, what do we always mean when we talk about 0 degrees? Well, it's in the same position as your x-axis would be on your rectangular axis. That's really all that's doing, is saying that this 0 degrees is in the same place as it would be there. We don't use the coordinate. We're just using that concept to fix that location. Does that help?
Yes, very much. And can I ask one other question about that? Is it like we just decided to call it X and put it and compare it to the XY axis, but it could have been zebra, and everybody say, hey, now we know it's zebra. Like it's just a matter of having the same mathematical picture in your mind.
That's
right?
all it is. Yep. And so some people won't even put the X in. They'll just say, this is my polar axis. This is 0 degrees. Yeah.
Okay, thank you.
Does anybody else have any questions for Kirsty about those first 3 parts?
Is there a simple answer for what exactly theta is?
It's any angle. It's just, instead of saying the angle every time, we say theta. And then it's going to have whatever degrees that particular angle is. So theta could be 35 degrees, theta could be 45 degrees, 16 degrees, 172 degrees. It's just that it's going to be the radius plus that angle.
Okay, thank you.
So all the way to the right, and then, I'm sorry, we don't have to go all the way to the right. We can stay right here. Is there another question?
Well, I'm just trying to figure out how I mean, this is like there's a connection to vectors, right? With this, because that's when we have magnitude and direction. And
so I would think that so.
So everything, right? I can express a vector both with rectangular and polar, and we're going to see that. You're going to practice being able to say, hey, my vector might be over 3 up 2, right? And I'm still giving it direction and a magnitude. Or you could say that it is 4 to 5 units long. I should have picked a degree that I knew, but let's say 2 over 3, that's less. So let's say it's going to be about 35 degrees, right? I'm just going to make that up. So that same point or that same vector can be described with rectangular coordinates or polar coordinates.
And you'll see that I just looked, there are vectors on the polar coordinate system on chart 4. So there is some reference to vectors also.
I wish I had this when I tutored challenge 4, because now that I'm seeing this picture, I'm like, it makes sense. Like, yes, you do this fancy math to go between your rectangular and your polar coordinates. But when Kirsty just said that, of course, that makes sense.
It's beautiful how they overlay on each other, right?
Yeah, but
the same place with different ways.
Yeah, but when you're doing it in physics, you're just doing mathematics, and so you don't get it. You're just confused by doing the computation.
In that sense, you could maybe create some of your own charts as you go in challenge 4 in physics. So it looks like we're pretty much
I have
out of time, and Kirsty might have, so if there's anything else you want to do, I will not try to keep going through these lessons.
Can I ask a question?
Yes.
So on the complex notation, in the center is 0, 0, 0, right? But why that is a plus bi instead of a and comma bi?
So it really, and I think that this may have been updated, and I'm not sure if it's made its way to the errata. So Babs, maybe you will take a note to check, but this really should be 0 plus 0i, right? That's going to be our origin. We would still express it as the plus, because it's 0 plus 0i. There's just one number there. So good catch there. All right, so we are, as always, happy to answer any questions. So you're welcome to speak up or raise your hand, and we can stay on this page. We can go to a blank page. So you're welcome to ask whatever questions you have. I will, while you're thinking of your questions, I am just going to remind you that we always finish up with our logic catechism, right, where we ask our kids, and our tutors are still doing this, right, all year, reminding the students what their resources are. And so remember that you too have resources, and our upcoming lessons you're going to see here, we're going to be continuing to work through this idea of geometry, and especially this idea of analytical geometry, where we're going to look at shapes that are in our coordinate plane and shapes that are just in our plane, our non-coordinate plane. And I think you're also going to start to see that we're going to have this, as Jill pointed out, right, the 2D, we start to get a sense of rest. And some of the lessons are going to be more restful than others. But Lee was intentional in trying to organize the lessons so that some of them would feel more restful for families and not intense every single week. All right, so I'm going to stop there and I'm going to open it up to questions.
Would you mind going back to the catechism slide? I just want to grab a question I never saw before. Thank you.
I have a question about page 3 in this booklet that we're doing right now. At the very top, it says shade the range. And then there's a beautiful shaded triangular looking thing. I don't get it. Can you explain how you got that? I was trying, my brain was doing flip-flops and it wasn't catching anything.
All right, so I'm going to open up, Labs had this beautiful idea to use a separate whiteboard, and so hopefully it will be a little bit clearer. So let's look at, we have two equations. So I'm going to move you guys over to the side so I can write over here. Our two equations are y, there we go. Y is greater than or equal to the absolute value of x plus 3 plus 2. Okay. So if we were to look at the line or the equation that this is describing, I could use something that looks like this, right? And I could say, okay, when x is 0, y is 2. If x is positive 1, then it becomes 4 plus 2 is 6. If it was negative 1, it becomes 2 plus 2 is 4. And your students might need more than that. But for me, I recognize that I've practiced that the absolute value of x gives me this picture, right? And so I look here and I say, okay, I'm going to graph this first of all. And so when x is 0, y is 2. When
Can
x
I
is
jump in
1,
there and say, you lost me at when x is 0, y is 2. Why would, if 0 plus 3,
well,
the
you're
absolute
right.
value is...
You are so right in that, because yes. see. Thank you. So let's go back here to this. And when X is 0, Y is actually 5. And so I see here that at 0, 5, and then 1, 6 is going to be here, and -1, 4 is going to be here. And so I sort of start to see what this is going to look like. Now I might keep going, right? Because I can see it's going in my positive direction. So I need to figure out where does it kind of turn around, right? Well, you might notice here that it's never going to be negative. And so I'm trying to figure out, so I'm going to just keep going to -2 and -3. And at -2, I end up with 3. And at -3, I end up with 2. And if I went to -4, now I end up with 1 + 1 is 3. And so here I've identified that this is going to be my turnaround point. For what it's worth, I think that this has actually been simplified in the new version. So this is why it's in gray in your lesson pages. I'm just working through it for here. So when X is -3, Y is 2, and then I know it's going to go this way. So there's my V, all right, because I know it has to be a V because it's absolute value. And now I look at the fact that it's greater than or equal to. So since it's or equal to, I'm using a straight solid line to say it could be on that line. My solution could be on that line, but it could also be greater than or above that line, right? So when X is 0, Y has to be at least 5, but it could be 6 and 7 and 8. And notice now all of the values that are above here are possible solutions to this inequality. So that's why I'm shading. So let's look at the next one. We have Y is less than or equal to 1, a little bit simpler. Right. So here we go. If I was to draw my graph, here's my Y = 1. Again, it's an or equals. So it could be a point that's on that line, but it could be anything that's below that line too. That would be less than 1, right? So all of my Y values. Does that help, Tanya, to see why we're shading the way we are?
Yeah, I think the one on the right seemed like a little more clear. So the one on the left, you would have to kind of fill out the XY chart and substitute some values in to be able to determine where that shading goes. It's not intuitive by looking at it, is my point, right? Or is it? Did I miss that?
The XY chart I did was just to help me figure out where my graph, the line was.
Okay.
So whenever I'm dealing with an inequality, the first thing that I want to look at is, let's look at another example. I'm just going to make one up.
There's one on the side too that goes in sort of a different direction on that same graph.
Well, the Y - 3 less than
yeah.
Well, okay. All right. So I'm gonna do 2, and then I'll come back to that one. So let's say I wanted Y is less than X. Let's look at one that's pretty familiar to us if we've been doing math, right? So as parents, the first thing that I want to do is I want to say, okay, what is my related equation? Well, my related equation would be Y = X. How do I graph Y = X? Well, in this case, notice it's not an or equals. So the Y = X is not a solution, but the line, I need to graph my line. So I'm going to use a dashed line. So you're going to see these dashed lines when it's not or equals. So this is like the open circles we did in 1D, right? Where we left the circle open. The dashed line is kind of like having that open circle. So that's step 1, is to graph my line. They're open or right, either the open version or the closed version, depending on whether it's an or equals to. The next thing, all I care about is this. Is it less than or greater than? If it's less than, it's going to be below the line. That's all we need to know, right? So my second step is that if it's less than, I'm shading below. If it's greater than, I'm shading above. let's look at our y, the absolute value of y minus 3 is less than x. And for the sake of time, I'm going to let you build an XY chart at home to see how this would graph. But it is going to be the absolute value on its side. So we're going to be tilting it on its side. And we are going to be moving it 3 units up. So 1, 2, 3, and it's going to look like this. But notice it's not or equals. So I'm going to make my line dashed. And now I want to know this has to be less than x. So in this case, right, so we're dealing, these are a little bit more challenging for us to think about, but where are those values going to be less than x? Well, they're going to be less than x to the left. So I'm going to shade to the left. And I can check that because if I said, okay, well, if y is 0, right, -3 has to be less than x. So at y equals 0, right, this has to be less than, right? I want everything that's less than that.
Yeah, I think in the answer key, it shows the opposite shading.
Let me look.
Like it shows like the little triangle to the right full
Yeah,
of shading.
it does. Yep.
So
that may be an error in the answer key then.
Oh, okay.
Let me look real quick. Yes, because if my, oh wait, hang on, let me think, because I may have just lied to you because I'm thinking about the x values. So
Greater than, it's x
let
is
me
greater
undo
than.
this.
X is greater than.
Right, so where is y less than x? So my y is, would still be.
Is it supposed to say greater than?
Your x is greater
No.
than.
X is greater.
My x is greater than this. Yes,
Oh,
thank you.
yes.
That makes all the difference in the world. If we were to rewrite this as x is greater than the absolute value of y minus 3, which is really whenever we have something in terms of y, that's what we should do. I'm going to be honest with you, Lee really likes to switch up the order and make you think out of order. As a math person who has been so trained to say, like, my variable and then what's in terms of, I always like to think of it this way, and I try to think Lee's way, and it doesn't always work well, as you see. So if we think about my x values now, where is x greater than that, it does make sense that we would be shading inside. Thanks, Jana. I think you were the one that just pointed that out. So thanks for saving me.
Isn't it the same thing no matter how you write it though? I mean, if you put the x first or the x after?
It is. It's just for me.
Okay.
It's just me. I struggle to think about the y minus 3, the absolute value of y minus 3 being less than x. Like I have to do a lot more mental gymnastics than thinking about x being greater than. Which is why Lee wants people to think both ways because, right, it's good for our brains to think both ways. That's just one of my limitations because I've been so conditioned to think one way. So, yes.
Thank you so much.
You're welcome.
So if we want to teach ourselves, speaking for myself, teach ourselves how to do this, and then our 7th grader, do we have a resource for those of us who wouldn't look at this and go, oh, I understand that this is going to give me this shape? Because I look at this and I'm mystified, and I'll be honest, I just copied the shading from the answer key because I had no idea what to do.
So really, that's your best way, right? That is the best, like that is the first time through when you look at this and you go, I don't know. Well, when you go and you look in the answer key and you go, okay, well, it's a sideways, right? Absolute value, it's a sideways V. well, absolute value, maybe that makes sense because my absolute value with the X inside, right? It gave me a V. So I still have a V. It's just on its side. I don't really understand why, but maybe I'm going to connect those ideas, right? And maybe I'm still not sure about that whole shading thing, but I'm going to go, okay, for now, I'm going to trust, right, that that this is true. And now the next time I come through and I see this again, you may not need to look it up in the answer key. I do try to go through this in the companion. I try to work through these exercises. As you can see, I did so well, just doing it blindly, that maybe how I did it in the companion isn't going to be helpful. Hopefully it is, but you can always go and look at these page tops for 1 through 4. I do work through them in the companion and try to explain them as I'm working through them. And then if you look in the charts, there's more detail in the companion for the chart. So if you find the section of the chart that talks about absolute value, you can go and click on that in the companion and see where see what additional information there is. And if that still doesn't help, you can come here and ask us on Wednesdays, or you can email us at themathmap@cc.com, and we'll not only try to get you an answer, but as we get some of those questions, as we see some duplicate questions coming in, I try to go back and add that content to the companion. So we are trying to learn from you where our most pressing questions are.
Okay, thank you.
I have a question and then like an aha moment that I would like to share. So maybe I'll do the aha moment first, and that is like you've been over the weeks you've been talking about saying things correctly, like the 0th power or the 5th power versus the power of 5, and I just couldn't get it. I was just like, I'm gonna just sit and stare at this every week until I figure out what she's talking about. And then I think it just kind of came to me. I once heard someone say, the power of life and death is in the tongue. That's in, one of the scriptures in Psalm or whatever. And then I realized that it doesn't say the power of life and death is in the tongue. It says death and life is in the power of the tongue. And suddenly I understood what you were talking about. It's like assigning power to the wrong thing. I don't know why that feels like a really cool aha moment for me, but it suddenly made sense, like, oh, we're ascribing power to the index as opposed to recognizing that the index is what gives us whatever we need to create the power. Is that right? Am I saying that right?
Beautiful. And Nicole, can I just tell you, like, that to me right there that's what we're all about. And like that just made my whole year that you just said a Bible verse helps you to understand math. Right? But it was a Bible verse, right, that you were seeking God, and he said, hey, this thing you've been thinking about, let me give you some insight here. And that's what we haven't done. I don't know if anybody's really ever done that with math, right? Certainly not in recent memory in the curricula we have available to us. And so I just love the fact that God did that for you. And you're right, we're wrongly ascribing power. And I think that was a beautiful thing. So
well, that was my aha moment. And I realized, okay, so we've been calling. So I think what you said was like exponent is the type of problem that we're doing. The index is actually the little number, right? Is that right? So
yeah.
Like the addition sign, it tells us we're doing addition. The subtraction sign tells us we're doing subtraction. The index tells us we're doing exponents.
When it's written as an exponent, yes. It's that place where it's written. Yep, that's exactly it.
Okay, that makes sense to me. And then I can move everything around and be like, okay, this one's a logarithm, this one's right.
Yep.
Okay,
that's it.
So this past week, I know that was supposed to be like week 3, but week 7, I got it. So that was really exciting to me.
Thank you for sharing.
And then my question is, and maybe if you can do it succinctly, that's great. But if we need to do it another time, that's fine. I'm having a hard time explaining, even though I think I understand, the difference between absolute value and cardinality. So if maybe you have a way that that would help me be able to express the difference.
Sure. So here's another example of where math education has kind of done us all a disservice, because it starts off by saying, well, just the absolute value of a number is always its positive, right? And that's what we're taught. It just gives you a positive. Well, really, absolute value is always going, whatever is in here, it's always telling us a magnitude. So if I say 3, I'm really saying what's the distance or the magnitude of 3, the distance between 3 and 0. So if I was to look on my number line, right, it's 1, 2, 3. That's my magnitude, right? So if
magnitude, distance?
Magnitude or distance, yep.
Okay.
It's size, right? I'm using magnitude to give you that idea of size, because we're going to come back around to cardinality. So this is really saying, what's the distance or magnitude, right, between -3 and 0? 3. It's still 3. Right? So now, what if I said this? What I'm saying is, what's the magnitude or the distance between -3 and 3? Well, it's 6. So now if we think about the fact that in 1D with numbers, we're always just talking about a distance on the number line, we're going to see in, I'm going to move my thing. Yes, I can do this. We're going to see when we get to 2D, if I have a vector, guess what? The magnitude of that vector, and don't stress about this necessarily, but it's going to be a squared plus b squared if this is a and this is b. Right? Because what I'm looking for is this distance from 0. So I write it with my absolute value, but I'm still talking about the size. Then we're going to see when we get to lesson 27 and we talk about real and imaginary numbers, right? And I have a plus bi. Well, guess what? This is b, this is a, and the absolute value of a complex number is going to be the square root of a squared plus b squared. And then, right, we have this idea. So we keep talking about this idea here of magnitude. And we say, okay, well, when I see it with a set, what do I mean? I'm still talking about the magnitude of the set, which just happens to be the number of elements. And then you're going to get to matrices in a little bit, and you're going to see that determinant is going to be taking that matrix, and it's going to be writing it with absolute value symbols. And it's a little bit different, and it's not an idea that we're even going to explore deeply in the math map, because it's really kind of beyond where we're going to push our students' brains. But this is a form of magnitude also. And so whenever you see what looks like absolute value symbols, it's always going to be telling you what's the size or the magnitude of the thing that I'm looking at. And if we help our students to see that, I think you're going to see that it's going to connect this idea of absolute value of a number to the absolute value, right, the magnitude of a set being cardinality. That it's really all that symbol is really telling us always the magnitude or the size. Does that help?
So if I if I tell my seventh grader absolute value is about absolute value is usually about a number, and cardinality is usually about a set of numbers or a set. Would that be correct?
Yep. Well, so no, well, yeah. So absolute value is the term we use when we're talking about numbers. Yes. And cardinality is the term that we're using when we talk about sets. And they both use that same symbol to talk about size or magnitude.
Size, distance, magnitude, all of those kind of measurements of how far something is from an origin or from a set point.
Yes.
Okay. But I would not be misleading her to say the most simple difference right now that you need to understand is that absolute value is about a number and cardinality is about a set.
Yes.
Okay.
That's correct.
That's helpful. That's very helpful.
All right,
Leslie
Leslie, I see
Leslie
your
has
hand.
patiently waiting. Leslie's been patiently waiting for a question.
This has all been good. I love everyone's questions. Okay, my question, it's a little clarification maybe. It comes from the division booklet number 6. And I'm on page 9 on the bottom where it says realize the denominator.
Yes.
So this thinking has to do with, and now I don't know if I'm gonna say it right, I to the power 4, I to the 4th power. So that whole concept, I to the 4th power, is really, we're thinking I squared times I squared. And I know that I equals the square root of -1. So I guess my question is so if we have I equals the square root of -1, is the inverse of that I squared equals 1?
I squared equals -1.
-1? Okay, that's what I couldn't remember if it was going to be a -1. So I squared equals -1. So then I'm just trying to help students break down the I to the power 4. So then we're taking I squared times I squared. And we know that I squared equals -1. So we have -1 times -1, and that's how we get to the positive 1.
Yes.
Denominator. Okay. So I think the struggle was seeing the steps of what we're doing between that I to the power 4 and then it becoming a 1. So I just wanted to make sure that I was computing that correctly in my head.
So I'm going to just throw this out there for anybody that is still kind of maybe unsure about complex numbers. Keep in mind, had you been doing other domains, you would have gone through lesson 27, which is all about complex numbers. So
Okay.
if you're like, hey, I just wanted a little bit more here about complex numbers, I would recommend, if you haven't done the naturals for lesson 27, go back, do the naturals for lesson 27, and maybe pull out your charts, especially the chart 2 and chart 3. And it's, I think, going to help fill in some of your blanks. Because what we've done in 1D is we're looking at complex numbers and really just imaginary numbers in a very arithmetic way, when they are really a very geometric number. And so if you haven't seen it geometrically and you're just looking at arithmetically, then you're correct, right? I can say that the square root of -1 times the square root of -1 is going to yield my radicand, or -1. And if I multiply that by another I, then I have -I. And then if I was to multiply that by a -I, I'd end up with -1 times -1, which is I. In lesson 27, we're going to look at that geometrically, and I'm going to show that to you now because I think it may help you to connect the dots and maybe even take this back to your students. So if I think here, I've got my real and my imaginary. If I was at 1 and I went 360 degrees, right? If I go 360 degrees, I end up back at 1. If I only went 180 degrees, where would I get to?
-1.
-1. And if I went another 180 degrees, where do I get to?
Back to positive.
Back to +1. And so we go, okay, so if multiplication is this idea of rotation, and I rotate 180 degrees, I'm essentially rotating by the -1, right? So 1 times -1 gets me halfway around my circle. And now I have to multiply by -1 again to get my other 180 degrees, and I get back to 1. Well, now what happens if, right? So that's where I see the square root of a 1 can be -1. Well, now what happens if I only want to go 90 degrees? Right? So if I want to go 90 degrees, I need a number that when I go another 90 degrees equals -1. Right? So I want some number times itself that equals -1. Is there any real number times itself that will give me -1?
No.
No.
And I see a
Can I ask,
graphic.
why is it not just half of the number? Why does it have to be a square? Why does it have to be a number times itself?
Because if I'm gonna go 90 degrees, right, and then I want to go another 90 degrees, it has to be the same amount.
Gotcha.
Right. So I'm gonna multiply by a and by a again to get to -1. But notice that there is no real number, right? So a in this case cannot be a real number. And so instead I go, okay, well, if a squared is -1, then a has to be the square root of -1. So that if I multiply by the square root of -1, I get up to here. And if I multiply it by again, I get to -1. And that's where, somewhat derogatorily, Rene Descartes said, okay, it's an imaginary number, and they started using the I. Okay. So this point here is my I. So if I multiply by I get up here on my imaginary axis. If I multiply by I again, I've gone 2 90-degree rotations and I'm at -1. Right. So let's do this. If I go 3 times, right, I multiply by I 3 times. Right. So that's essentially I cubed. But notice, where am I? I'm at -I. And if I was to multiply by another, rotate another 90 degrees, where do I get to?
1.
I have 4 90-degree rotations, but I got back to 1.
This is
And
so
would you
helpful.
express -I as negative the square root of -1, or the opposite of the square root of -1?
Yeah, it would just be negative square root -1. Yep. Does that help, Leslie?
Yes, I love the visual with it because I'm a visual person. Thank you so much.
You're welcome. Yeah, and again, if you look at chart 27-2, and then, like I said, maybe work through those naturals lessons, I think it'll emphasize this idea of rotation for you.
Okay, thank you.
You're welcome. Isaac, Asher, and Lydia, do you all have a question or just one of you?
It's just me. It's the mom, but I don't change my kid's screen name. I'm looking at page 3 in booklet 9, straight lines, in the middle section, the vertical line test. And I have a question about the piecewise graph. I'm not sure why it's not a function. I can see why if the points were both inclusive, it would be not a function, but it looks like because those points are both exclusive, that the vertical line doesn't intersect the graph twice. Can you
are
help me understand
correct.
that?
I think that is an error that we already corrected.
I must have missed it in the errata. Then I looked and didn't see it.
Sometimes we correct things and right after they've updated the errata, but
okay.
Babs will make sure that has been corrected.
Okay.
Yeah.
So should I fill the points in my booklet then?
You could either fill in your points and then say it's not a function, or you could change your answer and say it is a function.
Okay, either way. All right.
Either
Thank
way.
you very
Yep.
much.
You're welcome. All right. Any other questions?
Yeah, this is Peggy, and I'm still back in division, and I had a couple questions, and they might be really easy, but I don't get it. So in the division book, page 7, at the bottom, it says list the prime factors, and for 18, it's got 2 times 3 times 3. And I get that because those are the prime factors. But then when I looked in the answer key for 20 or for the 3, I wrote the prime factor was 3, but it says 3 times 1. And I've always been taught that 1 is not a prime number.
You're correct. Yes, I know. And we've had this question.
Okay,
I've had
I'm
this
sorry.
question from a couple of people
I'm sorry.
because you're right. 1 is not a prime number. And so its prime factorization isn't really a 1 times 3. It would just be 3. But when we're starting to look at GCFs and LCMs, a lot of times we'll write that 1 in just so that it's kind of like the hidden 1, right? That 1 is still there, not necessarily as a prime factor, but as the unit that we're working in. And so when we're dealing with GCF and LCM, a lot of times we'll, especially GCF, we'll use that 1 because sometimes that is our greatest common factor. And that's a really unsatisfactory answer, because I know you're sitting there going, but it's the prime factor, so it should just be 3. And I agree with you. So I will, because Babs is so good about keeping track of all these things on our book club, and Shauna, I don't know if Shauna's on today, but I did see Babs, so that's why I keep asking her. That maybe we'll go ahead and look at changing that. But again, a lot of times, especially if we're looking at a prime number, we'll write it with the 1 just to remind us that it's 1 in itself, even though 1 is not prime. So not a satisfactory answer, because you're correct. But one of those, where we say we're really specific in our language and math, and then we do things that break the rules. So
I did have one more question on page 8 in the top right corner. I tried to wrap my brain around this and I couldn't figure it out. It says divide the limits and rationalize the denominators. And so the top line, I think I'm reading this correct. The limit of f of x over g of x as x approaches a. Did I read that correctly?
Yep.
Okay. But then you go over to the right, and the numerator is the limit of x as x approaches a over the limit of xi as x approaches a. And I don't understand where the I came from at all.
That's just telling you that that's the function. That's all that means, is it saying, okay, if I wanted to, for example, in the complex plane, first let me be clear that in the complex plane, we do not set, there is no function between the reals and the imaginaries. We don't graph in the complex plane. They're just numbers. But if we're not graphing, we're not talking about graphing. If I said, what is the rule or the function that maps the reals to the imaginaries, right? So if I said, what function does this? I could say, well, if x is my real number and my function of x, right, says to multiply it by I, right? So then now xi is my imaginary number. And so that's the rule that just says every real number can be multiplied by I to give me an imaginary number. That's essentially the function that they're putting there. So it's just, instead of g of x in this case would have been x times I. That's all that means.
That's beyond my math brain, but I'll accept it and try to run with it. Thank you.
All right. Anything else? Any other last minute questions before we jump off?
Am I correct in saying that what you're saying is that all of, whether it's imaginary or a variable or an apple or a ladder, you can still do the same function with it? That's what that is trying to show you.
That's all that's just trying to say, hey, look, I can write this, those are just kind of arbitrary functions just so that you can have practice operating with, right, realizing the denominator eventually at the same time that you're practicing limits. That's why Lee chose that function. So it's just, she could have said x squared or 2x or x plus 3, right? She just decided to do x times I as her function there.
Okay. Okay. I have a bit of feedback that I got yesterday from a Challenge A class that I'm curious about. One of the kids, he enjoys the math map. It's fine, but he also really loves Saxon, and so his mom didn't really have a hard time transferring him over to the math map, as far as he wasn't very resistant or anything like that. I have a bunch of resistant people in my community, but this kid actually asked to go back to Saxon for one reason. He said, I just want to do more problems. I just want a list of things, because he just got the satisfaction of saying, I just did 15 problems and got them right. And so I just wanted to give that feedback and ask, I know that I'm assuming that they could probably find more in the companion. I haven't looked. Is that true? They could find more just like problems to do in the companion, maybe. But even that, when I suggested that, they were like, who wants to keep having to go back and print off more things? So I don't really know how to
So
answer
really,
that.
yeah. So one of our earlier book clubs, I think Abs can maybe remember which book club it was, where we talked about adding in more computation practice is really what he's looking for. That there are no drill sheets in the companion, but because Lee is kind of like, well, just use, cards and dice to generate, right, an infinite number of problems. So for example, if I'm trying to think of like, let's say that he was like, I really like doing this and I just want to practice realizing the denominator, right? So maybe in the lesson pages, what he sees is all he's doing is 4 over I, 3 over 2I, right? Maybe those are the two problems and he wants more. Well, this is where I would say, okay, well, look, just decide that this is what I'm going to do, and now either roll a dice or flip cards. And if you flip cards, the beauty of it is that I can have multiple digit numbers. And so I could have like, I could flip 45 and 26, right? Using cards. I could flip and I could make that more difficult, right? So if I had a student who's like, I really want to practice complex fractions, maybe I flip my cards and I flip them in this order. So I can make, using cards, I can have an infinite number of ways to practice those same things that I'm practicing on the lesson pages. And so that's really, I think, a better way, because you can do that, right? Instead of, I know some kids have been trained because they like those sheets and I get through it, right? We've trained everybody to think that math success is getting through those drill sheets. And it's one of the things I want to talk about when we get to lesson 15 and we talk about assessment, because we've all been trained that success in math is calculation and getting 100 on a test, even if you don't really understand it. But doing this, using cards or using dice, lets us actually practice these specific concepts in an infinite number of ways. And I think it kind of makes it a little bit more fun. But
so I think it would be, so just going off of this, because I can just hear them now saying, oh, so now I have to make up my own problems too, right? But what if it were like, the mom says, okay, once you finish this, I want you to make up 10 problems and answer them yourself, because he wants a finite number of problems so he can feel like he has had a success.
I think that's a perfect response. Yeah, I think that's a perfect response, to challenge him to go and use cards so you get generic numbers or random numbers, and then take that and make up your own problems to solve. I think that is a great thing to give to students, because that's how we learn, right? That's what Nat Bowditch did, right? He said, okay, I want to do this. Well, let me try this with different numbers and see if I can can figure this out. And so we're
And then
enabling
I
our
can still give him a finite number of say, hey, I want you to make 10 problems up. So then he doesn't feel like, when am I
infinite.
finished? Right.
Right.
Yeah.
That's a great idea.
I love that. Thank
Babs
you.
just
I
put that
appreciate
link in the chat log there. So if anybody wants to go back and look at that book club where we talked about some of that in detail, that may be helpful.
Great.
All right. Well,
Great.
I think that we have been kicked out because Emma needs the Zoom room. But if you have questions that can't wait till next week, please email us and we'll get you answers as soon as we can. Jill, thank you for doing such a great job of leading us today and just demonstrating that you don't have to be me and have all the math answers, right? You don't have to have written the curriculum in order to tutor this. You did a great job and I thank you for that. And Jill and Babs will both be back as guest leaders on other weeks. So look forward to that. All right. Thanks, everybody. Have a great week.